And our next talk is by Yana Khusanova. Yana, would you like to share your screen? And the title is The Host Galaxies of Radio-Loud Quasars at Redshift Greater Than 6.
Yeah. So I hope you can see my screen.
Yes,
is all right? Okay, great. So first of all, thank you very much for organizers for giving me this opportunity to give this talk. And today I'm going to talk about the recent results I obtained with NOEMA observations of the host galaxies of radio-loud quasars at redshifts above 6. So this is exactly the redshifts where we observe the epoch of reionization. And at these redshifts, in the recent decades, hundreds of quasars were discovered. And now we go as far as to redshift 7.5. But most of these quasars are radio quiet. And only 5 from the quasars at redshifts above 6 are radio loud. And the highest redshift of the radio-loud quasars is currently 6.8. It was a recent discovery by Eduardo Bañeras. And compared to radio-loud quasars, the host galaxies of radio-quiet quasars were extensively observed with ALMA and with NOEMA. And we can observe the farthest frame-far infrared continuum. We can observe the C2 emission lines, and both of radio-quiet quasars are detected. So they are in star-forming host galaxies, but little is known about the host galaxies of radio-loud quasars and how the feedback from the jet is affecting the host galaxy. So in order to determine if it's quenching the star formation or it's enhancing the star formation, we need to observe these quasars. And recently we observed 4 quasars. One is missing. It is also a recent discovery. But 4 of them are observed with NOEMA. And these are the summary of the results of these observations. You can see the continuum images on the top panel and the C2 emission line images on the bottom, on the middle panel, and the spectral profile of C2 line emission at the bottom. So the interesting thing is that it seems that all these quasars, they are kind of in 2 completely different groups. There are 2 of them which are very faint, and in one of them we don't detect neither continuum emission nor C2 emission, and 2 of them are very bright. And even like in this one, in this quasar where we observe some C2 emission, this emission is still much fainter than for this 2 on the right panel. And the brightest ones, they look very similar. They have like almost the same continuum emission and almost the same C2 emission. But the question is like why these radio-loud quasars are kind of like in these 2 groups with very faint and very bright. If like in some of them the feedback is suppressing star formation, or in other ones are enhancing star formation, or there's some other explanation. So if you look at the brightest quasars from the sample, they're not just the brightest in the observations of the C2 line emission and millimeter continuum emission. They are also the brightest in the X-ray, and they're also the most radio-loud quasars from the sample. And one of them actually was like this one is a blazar, while the other one is not confirmed as a blazar, but it's outshining the blazar in the X-ray. So these 2 objects, they have extreme properties in the X-ray. They are the brightest at redshift above 6. And we know that in the radio the C2 emission comes primarily from the photodissociation region, so it's linked to the star formation. But if in these 2 sources the C2 emission is coming from the X-ray dominated region, then this would explain the difference between the two groups. Maybe the C2 emission in these two brightest quasars is actually not related to the star formation, but related to the X-ray dominated region. And then without the radio jet, we would observe, if we would subtract this part which is coming from the X-ray dominated region, then we would also observe fainter C2 emission. I think I went to the different slide, sorry. So next, let's look at the spectral energy distribution. And here the radio observations are shown as squares, and the fit to the observation is shown as dotted lines with the power law. And the NOEMA results are the field stars, and the fit to the NOEMA observations with the modified black body model is shown as the solid lines. But the problem is, first of all, you can see that there is kind of correlation between the brightness of the fine thread continuum and the brightness at the radio wavelengths, because like all of the quasars, the high is the radio flux, the high is the flux in the far infrared. But if we extrapolate the power law from the radio observations, then we can see that at least in one object, the contribution from the synchrotron emission can be significant, and this is in this blazar. But in the other object, which is also the brightest object, if we extrapolate the contribution from radio emission, it's not as significant. But still, like for these two objects, we don't know exactly if this far infrared continuum flux is coming only from star formation and from the cold dust, or there is some additional contribution which is not taken into account, and then the star formation would also be lower and maybe closer to the fainter objects. So they look very similar, but in the same time, these two brightest objects might be different. And finally, I want to show the plot with star formation rate estimates based on the fine thread continuum measurement and based on the C2 line. And here also there is a difference between these two groups, because for the faintest ones, the results from fine thread and from the C2 emission, they are consistent with each other. But there is a big difference between the star formation rate based on the C2 emission and star formation rate based on the fine thread continuum for the brightest radio allowed quasars. And the problem here is that there is still some uncertainty, and because these measurements are based on the modified black body, and if the fine thread continuum flux does not only come from the star formation and from the cold dust in the galaxy, then these measurements can be slightly lower. But there are also some uncertainties due to the uncertainty on the dust temperature and on the emissivity index. So if we assume that all these measurements which are shown here are correct, and there are no other effects which are boosting the fine thread flux and C2 emission flux, then the radio allowed quasars would be very similar in their properties to radio quiet. But if it's not the case, then it's likely that they have lower star formation rates compared to radio quiet quasars. And finally, I want to show again this plot with a summary and point out to the spectral shapes of the C2 lines, because interestingly, two of them have some signs of a double Gaussian profile, and this could be explained as a merger. So two of the radio loud quasars can be hosted by galaxies with undergoing merger, and one of them has a single Gaussian profile, and it's not clear if it is a merger or not because there are no high resolution observations. But it's also an interesting possibility that maybe the radio loud quasars are hosted by mergers. So I'm going to leave you with the summary, and thank you very much for your attention.
Thank you very much, Yana. We'll wait a little bit while people type up their questions.
Okay.
Okay, in the SED plot, is the source with large synchrotron contribution a blazar?
Yes, exactly.
And the second part of the question is, are your sources resolved by ALMA?
No, these sources which I show here, they were only observed with NOEMA. I don't have ALMA observations, but yeah, this is a possibility for the follow-up.
Next question is, for the SEDs, did you explore the effects of different dust temperature and emissivity indices on the far-IR-based SFR?
No, I haven't explored it, but this is in my plans to do it.
Okay, this is related to an earlier question. Are the sources resolved in the radio data?
Yes, and actually, like some of these sources which show some the signs of the mergers in the radio data, they also show two components. So it's quite likely that they are actually the mergers.
Okay. All we have so far, but we'll wait a little bit more, see if any other questions come in. Well, if any of you come up with more questions, we encourage you to put them in the Slack, and Yana can write back to you there. So thank you, Yana.